This is our third video on working with the dot product. One of the things the dot product is extremely useful for is creating a unit vector. So let's say that you have a vector, some vector that you know. For instance, it might point along the direction of a beam. It might point along the direction a particle is supposed to travel. And you want to find a vector whose length is 1 in that direction. So you just want to use this for direction and not for length. You can do that by creating unit vectors. We have lots of unit vectors, I, j, k. We also have r hat, theta hat, and phi hat in spherical coordinates. So physicists use these unit vectors all the time. The way to create a unit vector is actually rather simple. You know that a unit vector has a hat on it to indicate it has length 1. You just take a regular vector and you divide by its magnitude. Well, we just found a way to find that magnitude in the previous video, and that is we simply divide by the square root of the vector dotted into itself. So for any vector, I can find a unit vector by just simply taking the dot product of the vector into itself, taking the square root, and then using that length and divided it into the original vector. Let me show you how this is done. You have a vector A, and A has the things 3i hat plus 2j hat minus 4k hat, and I want to find A hat. Well, my first thing to do is to find the dot product of A upon itself, which is 3 squared plus 2 squared plus minus 4 squared, which is 9 plus 4 plus 16 is 29. So therefore A hat is equal to A vector divided by the square root of A dot A, which is 3i hat plus 2j hat minus 4k hat divided by the square root of 29. Or if you prefer, it's 3 over the square root of 29 I hat plus 2 over the square root of 29 j hat minus 4 over the square root of 29 k hat. So this is my A hat, if you would, x part, and this is my y component, and this is my z component, and we'll find out that those are actually related to cosines that the vector makes with respect to the angle. But anyway, given the vector, you can convert it into something that has a total length of 1 just by doing the dot product here and dividing by the vector by the square root of A dot A. Finding components of a vector. So it turns out that we often need to find components, and we do this using the dot product. Okay, so for instance, let's say that you had x and y, and we know that they have little unit vectors I hat and j hat. But there are other vector systems as well. An example of that is r hat in polar form and phi hat that goes like this. Or if we prefer, we can put it down here. We can use the dot product to write this r hat in terms of I and j using the dot product. And in fact, it looks something like this. We're not going to do it in this course really, but just as to give you an idea of what it looks like, r dot I hat times I hat and r hat dot j hat gives you how much lies along j. So this would be its x component, and this would be its y component. So if you have a set of vectors, unit vectors, you can break any vector up in terms of that by taking dot products. Let me show you one more example of that. Let's say you had a vector that was 3i hat plus 4j hat. Now it's obvious that the x component is 3. Watch what happens when you dot it to I hat. Well, you get 3i hat dot I hat, and you get 4 I hat, j hat dot I hat, but this term is 0 because the vectors are perpendicular, and this is 1. So what do you get? 3, the x component. So you can find a component of any vector by dotting it with the unit vector that you want to find the component. Let me show you one other kind of interesting thing that the dot product can do, something that especially is used by civil engineers. They often deal with three-dimensional structures, and for instance, they might have guide wires going from some sort of an antenna. And they might need to know what this length of this guide wire is, but they also might need it in Cartesian form, or they have x, y, and z. Well, what they'll do a lot of times is write it in what's called directional cosine. And what that is that they say, hey, look, if you take any vector, say a vector like this, that goes out in some way, call that vector A. That vector makes a angle with each of the unit vectors. Oops. Sorry, didn't mean that. I'm going to call that gamma because that's z. And it makes one back over here with the y-axis, beta. And it makes an angle alpha with respect to the x-axis. Doing what we did a minute ago, it says that AX is equal to A dot I hat. Well, that's the length of A times the length of I, which is 1, times the cosine of the angle. Well, the angle is alpha. A sub y is the length of the vector A dotted into j hat, which is the length of A times the length of j, which is 1, times the cosine of beta. And A sub z, the z component, is the vector dotted into k hat, which is the length of A times 1, which is the length of k, times the cosine of gamma. Now what that means is that you could rewrite our vector A as A cosine alpha I hat plus A cosine beta j hat plus the z component A cosine gamma k hat. And then they say, hey, look, those three guys have the same A. We'll factor that out. And I have the cosine alpha I hat plus the cosine beta j hat plus the cosine gamma k hat. Now what is this? Well, this thing is actually the unit vector, because the unit vector gives the direction and A gives the length. Now this kind of, I want to say, hybrid form where you have both a length and a direction, but you also kind of have it written as Cartesian, is known as the directional cosine form of a vector. And it's very useful, especially in engineering, where you're switching between Cartesian and polar forms. And you're dealing really in three-dimensional objects because the Earth is three-dimensional in our world, not two-dimensional as physics problems often have. So, directional cosine form of a vector. So, a minute ago when I wrote those guys up here that were divided by the square root of 29, let's see where they're at. These guys here were in fact the cosine. So this was the cosine of alpha, this was the cosine of beta, and this was the cosine of gamma. And if you took the inverse cosine of this, you could get me the angle at which the A vector makes with respect to the z-axis. And this would give you beta if you take the inverse cosine, which will give you the angle it makes with respect to the y-axis, and this would give you alpha. So you can find the angles and the lengths, or you can work with the components. Either way. This is far more than you'll need in this particular course, but there's no reason not to actually improve your vector knowledge. Math is really useful in college, and especially with vectors. And the better you are at it, the stronger and more likely you are to succeed in the STEM field. So that's it for this video. We'll move on to the important discussion now of applying the vector dot product and when we apply, scalar dot product. When we do that, to calculate something called work, which is extremely important in the field of physics.